we're going to walk through some more examples of the chain rule. If you look carefully at this first problem, you're going to realize we actually have to use the chain rule more than once. If you rewrote secant cubed of 2x minus 5, that would actually look like secant of 2x minus 5, and that whole thing is raised to the third power. So we can break this thing down. If you start at the inside, we could make this secant of something simpler than 2x minus 5. We could say u is 2x minus 5. Which would mean you could think of this as secant of u. Maybe we should write that. Y is equal to secant of u, and that is raised to the third power. Well, that's not so simple either. That would still require the chain rule, so we'll rewrite. Now, we can't write u equals. We've already written a u, so we're going to use the next letter in line. V is equal to secant of u, that input function. And so now you can think of what we have as y is equal to v cubed. Now, if you thought about the derivative of v cubed, that's pretty easy. That doesn't require the chain rule. Heck, that's just good old power rule. And so let's write that. dy dv is equal to 3v squared. So that's kind of the derivative of what we started with. But we expected the derivative of secant cubed of 2x minus 5 to have a bunch of x's in it. Can you get a derivative dy dx out of dv? Well, yeah, kind of, but I need to have a dv in a numerator to divide out. Let's get that in the middle. dv du, the derivative of secant of u, is going to be secant u tangent u. So we're getting close. If I multiply dy over dv times dv over du, I'm going to get dy over du, but I wanted dy over dx, so I need to take the derivative of u. So du dx is equal to 2. So dy dx, that's 2, times, oh, that's not dx, du dx, which is 2, times dv over du, which is secant u tangent u, times by over dv, which is 3v squared. That's actually the derivative we're looking for because the du's. Oh man, did I screw that up again? I'm sure you caught that. This 3v squared is dy dv. So the left-hand side would be dy over dx, 2, and then we don't want secant of u. We will replace that u with what u is equal to, so secant of 2x minus 5. Likewise with the u inside of the tangent, 2x minus 5, and then 3 times v squared. What was v? Secant of u. Uh-oh. I still need to replace that u. So let's erase the u and write what u is equal to 2x minus 5. So if we rewrite all of this, 3 times 2 is 6. How many secants are multiplied? 3 of them. So secant cubed of 2x minus 5 multiplied by tangent of 2x minus 5. Okay. That was a lot of thinking and a lot of writing, but that notation shows where everything comes from. You can check that on your calculator by, I don't know, asking your calculator to do a derivative of secant cubed of 2x minus 5 at, I don't know, let's say 0. And then substituting 0 into this final line and seeing if those numbers match. Later on in the year, you're not going to do all of that work. What would the work look like if we're doing a shorter version? Well, we work from the outside in. So later on in the year, what you're going to be able to do is just, oh, heck, I'll do y prime. I can use a different notation. Is we work from the outer function in. what's the outermost function? It's the cubing function. The derivative of something cubed is 3 times something squared. I want to go back and forth between these. Now notice what we put in that 3 times that something squared. It's what was originally cubed. We had something cubed, and it has a derivative of 3 times that same thing squared. So inside of here is going to be secant of 2x minus 5. Okay. But when we did that, we also needed the rate of change, the derivative of that v, which was secant, the next inner function. So the derivative of that secant of something is secant tangent. I have a plan for leaving those blank. Why did I do that? Because it really doesn't matter what that number, what that function is. The derivative of secant of something is secant of that same something, tangent of that same something, which is what I wrote. And that something is 2x minus 5, which has a rate of change of 2. Okay? I'm going to go through that again, saying the same things, writing a little bit quicker. So when we look at secant cubed of 2x minus 5, the outermost function is the cubing function. The derivative of something cubed is 3 times something squared. Our something is secant, and the derivative of secant is secant tangent. And since the original secant had a 2x minus 5, the input to secant, that doesn't look like a secant, is 2x minus 5, tangent of 2x minus 5. That 2x minus 5 has a derivative of 2. You'll notice when I switch back to what we did before, that's the exact same thing. Okay, how the heck do we do this thing? It's actually very similar. So what's the innermost function for cosecant cubed of 3x over 2? We're going to do this the long way. The innermost function, which we're going to call u, is 3x over 2. Don't get fooled. You don't need the quotient rule there. 3 over 2 is a constant multiplier, so du over dx is just 3 halves. Now let's try to imagine so we don't have to rewrite. Right now we would have cosecant cubed of u. So the next inner function, v, is going to be cosecant of u, which means dv du is equal to negative cosecant. That doesn't look like an S. Of u times cotangent of u. And then what would we be left with? We would be left with y is equal to v cubed. And dv is equal to 3v squared. So we're going to write du dx multiplied by dv du multiplied by dy dv on the left side. And then we'll make those matching things on the right-hand side of the equal sign. Du over dx is 3 halves, multiplied by dv over du is negative cosecant u cotangent u, multiplied by dy dv, which is 3v squared. So dy over dx is, let's multiply all the constants together. 3 halves times 3 is 9 halves. Bring the negative out front so we don't forget about it. Cosecant of u, and u is 3x over 2. Cotangent of u, and u is 3x over 2. Times, oh, not 3. I already took care of the 3. V squared, and v is cosecant. I do that every time, don't I? just like I switch pages every time. So v squared is cosecant squared, but I don't want to write cosecant of u. I'm going to put 3x over 2 in here. Oh, that looks pretty rough. Well, can we do this? What's the outermost function? Holy crap, it's a product rule. And the derivative of a product of two functions is the first function, x squared, times the derivative of the second function. Now that I am going to struggle with, so I'm going to leave a lot of room, okay? Plus the second function, which is going to be tangent of 1 over x multiplied by the derivative of the first function, and we know the derivative of x squared is 2x. So now I have to worry about the derivative of tangent of 1 over x. Pretend the 1 over x isn't there. The derivative of tangent of something is secant squared of something. Ooh, what's our something? Our something is 1 over x, which has the derivative -1 over x squared. If you're confused about the derivative of -1 over x squared, you can either use the quotient rule. I didn't do that. We did prove that the power rule works for negative exponents. You can think of 1 over x as x to the power -1. Ooh, find the first derivative of sine cubed. This I've got. This seems easy because this is only one function inside of another function. So I'm going to work outermost in. Well, maybe we'll do this the long way and then really quickly the short way. So y is equal to u cubed if u is equal to sine. dy du is 3u squared, and du dx is cosine of x, which means dy over du times du over dx would simplify to dy over dx equal to 3 sine squared x cosine x. Let's pretend this is a different timeline and we were just given y equals sine cubed of x. And we're feeling confident, we know what we're doing. We're just going to start off. The derivative of something cubed is 3 times something squared. Notice we have that on the left. That something is sine of x, which has the rate of change of cosine of x. Ooh, this sounds awfully similar. So the derivative of y with respect to x, we're working outermost in. Ooh, the derivative of something to the 4th power is 4 times something to the 3rd power. Our something is sine, which has a rate of change of cosine. The derivative of something cubed is 3 times something squared, and our something is tangent, which has a rate of change of secant squared. The derivative of something squared is 2 times something to the 1st power. Our something is secant, which has a rate of change of secant tangent. The derivative of something to the 17th power is 17 times that something to the 16th power. Our something is cosine, which has a rate of change of negative sine. The derivative of cosine of something is negative sine of something, and our something is x squared, which has a rate of change of 2x.